Permutation. Here is part 2 now. Um, Permutation is an arrangement of objects in a specific order. In permutation, order matters. This means that two arrangements containing the same objects but in different positions are regarded as different. For example, the arrangements ABC and BAC are different permutations because the order of the letters is different. The number of permutations of n distinct objects taking R at a time is denoted by n permutation R. This is the notation and is given by this formula. N permutation R is equal to n factorial over n minus R factorial. So what is factorial? N factorial, for instance, is n times the number before n, which is n minus 1, times the number before n minus 1, which is n minus 2, and you keep descending till you get to 1. Alright, and take note, 0 factorial is 1. So for factorials, for instance, 5 factorial will be 5, which is n itself. 5 is n. 5 times 4, 5 minus 1 is 4, 5 minus 2 is 3, times 3 times 2 times 1, like that till you get to 1. So 5 factorial will be 5 times 4 times 3 times 2 times 1, which is 120, I guess. Yes. And important notes: if all the n objects are arranged, then the number of permutation is n factorial. Right? If you have n objects that are well arranged and they are distinct, then the number of permutations is n factorial. We'll see examples anyway. If only R objects are selected and arranged from n distinct objects, then the number of permutations is n permutation R, which is given this way. Let's see. An analogy says that permutation is like arranging students in positions for a group photograph. The position of each student matters. You also have that at the back of your mind. So an example: find the value of 5 permutation 2. We have our formula for permutation to be n factorial over n minus R factorial. In this case, our n is 5, R is 2. So we'll sub all that into this formula. So that is now 5 permutation 2 is 5 factorial over 5 minus 2 factorial. 5 minus 2, of course, is 3. So this altogether is 5 over 3 factorial. 5 factorial at the numerator is 5 times 4 times 3 times 2 times 1. At the denominator, we have 3 times 2 times 1. 3 times 2 times 1 can cancel 3 times 2 times 1 at the numerator. So the numerator will be left with 5 times 4, which is 20. So 5 permutation 2 is 20 at the end of the day. I have a similar example with 7 permutation 3, which you can pause and check by yourself. It's the same thing. Another one, 10 permutation 1, the same procedure. Now let's see this one. N permutation 2 equals 30. We want to find n. Now we know that n permutation 2 will be n factorial over n minus 2 factorial, because in this case n still remains unknown and then R is now 2. Right? Now remember, our definition for n factorial is n times the number before n times the number before that, and keep descending to 1. So if we do that, n factorial will be n times n minus 1 times n minus 2 times n minus 3 times, right? But then we can stop the descending order at n minus 2, right? So n factorial at the numerator will be n times n minus 1 times n minus 2 factorial. When putting that factorial behind n minus 2 at the numerator implies that it still keeps descending, right? But we're stopping at n minus 2 factorial because we have n minus 2 factorial at the denominator, so they can cancel out. N minus 2 factorial will cancel out that n minus 2 factorial at the numerator, and that's why we are left with this n times n minus 1. And so we're saying at the end of the day that n into n minus 1 is equal to 30, because that's what we are told in the question, that our n permutation 2 is 30. Then what is n? We have simplified n permutation 2 to this, to n into n minus 1. We are saying is equal to 30. So we'll solve this quadratic. If we expand these brackets, we have n squared minus n minus 30 equals 0. Solve the quadratic. N will be either 6 or minus 5. But n cannot be negative, and so we'll choose the positive answer, which is 6. Right? We don't have factorials for negative numbers. Our n is taken from the set of natural numbers, only counting positive counting numbers. Next we have a case with distinct objects. If n distinct objects are to be arranged in a line, the number of possible arrangements is n factorial. That's straightforward. This is because there are n choices for the first position, n minus 1 choices for the second position because one position is taken already, n minus 2 choices for the third position because 2 positions, the first and second positions, are taken already, and so on until one object remains, which is this number 1 that you are seeing here. So for example, in how many ways can the letters of the word CAT be arranged? Or I like to use the word shuffled. How many ways can we shuffle CAT? You can see 3 letters are distinct, that is, no letter is repeated. And so the word CAT has 3 distinct letters, therefore the number of arrangements or shuffles is 3 factorial. 3 times 2 times 1 equals 6. These are the arrangements in the real sense. We can have CAT, CTA, ACT, ATC, TCA, and TAC. You can see 1, 2, 3, 4, 5, 6 different arrangements for the word CAT. That's what we mean by permutation. We have another similar example which I'll skip because of our time, and yet another one. Let me take example 2.8. In how many ways can 3 different positions of class monitor, assistant monitor, and timekeeper be assigned to 8 students? So we have 3 positions. We want to see the way we can shuffle it among 8 students. 3 posts are different, they are distinct, so order matters, hence we use permutation. So the simple formula that gives us the solution to this problem is 8 permutation 3, and 8 permutation 3 of course is 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial, which is 336. So in essence we're saying we can shuffle those 3 positions among 8 students in 336 ways. To another case where we might have repeated objects. When some objects are repeated and are not distinguishable from one another, the number of distinct permutations is less than n factorial. If among n objects p are alike or are alike of one kind, q are alike of another kind, r are alike of another kind, then number of distinct permutations is n factorial divided by those repetitions. Let's go straight to example 2.11. Find the number of distinct arrangements of the letters in the word two, T-O-O. The word two has three letters in all, of which T is unique, is distinct, but O is repeated. And so we have three letters. First, that's 3 factorial, and then we have one letter that is repeated twice. So divide by 2 factorial, and that's 6 over 2, which is 3. So the arrangements are 3, and these are the arrangements without repetition for that word. I hope you understand. You see that there are no other distinct ways of arranging this word because of the repeated letter. Let's see. Look at this example too. We have the word level, L-E-V-E-L. L appears 2 times, E appears twice, V once. And so because the word has 5 letters, we'll have 5 factorial, then we'll divide the repeated ones. We have one letter repeated twice, another letter repeated twice. So we'll divide by 2 factorial times 2 factorial. 5 factorial is 120, 2 factorial is 2 times 2, which is 4. 120 divided by 4 is 30. Circular permutation. This circular permutation is the arrangement of objects around a circle. In circular arrangement, there is no fixed starting point. Arrangements that differ only by rotation are considered the same. For n distinct objects arranged around the circle, the number of circular permutations is n minus 1 factorial. One object may be fixed in position and the remaining n minus 1 objects are arranged around it. If objects are arranged in a circle, it's impossible to shuffle correctly if you don't have a fixed starting point, and that's n minus 1. We always subtract one of the objects to serve as a starting point, and then the other objects will be shuffled around that fixed object. And so we have example in how many ways can 6 students sit around the circular table. For circular arrangements of n distinct objects, we have the formulas with n minus 1 factorial, so it's simply 6 minus 1 factorial, which is 5 factorial, which is 120. Next example is similar, and we have the following exercises. So thank you.